Ladies and gentlemen, please welcome Jean-Philippe Auvoic.
Good afternoon, everybody. I'm Jean-Philippe Auvoic, President-elect of Tectonophysics, and I have the honor of chairing this centennial session on seismic and volcanic hazard with my colleagues Michael Manga, Josh Jones, and Wenlu Zhu, who is somewhere in here. So we have assembled two panels. The first panel will focus on seismic hazard, so we're going to focus on that theme for 1 hour, and then we will move to volcanic hazard for another hour. So the panel is constituted of very distinguished researchers in that area, and we have the privilege to have with us today Ross Stein, who's going to give us an overview of the theme of seismic hazard, and that the other panelists will be focusing on special topics. And I hope we'll have a lively discussion by the end of the presentations. Thank you.
Thank you, Jean-Philippe. So I want to focus on forecasting from seconds to millennia, and then I want to focus on how we can capture seismic hazards worldwide in the best possible way. Now, just six weeks ago, a seminal moment happened for earthquake science when the governor of California announced the launch of the MyShake app. Now let's see, can I make him speak? Do we have sound?
The site of the old Bay Bridge here on the Oakland side of the San Francisco Bay. 30 years ago, on this day, a portion of this Bay Bridge collapsed in the Loma Prieta earthquake. I was living in the Marina District in San Francisco, down on Rico Way. I remember it like it was yesterday. 3 decades later, proud to announce that we finally have an early earthquake warning system that now is operational. And we're encouraging people to download the MyShake app. Our goal is to get 4 million people to download this app by the end of 2020. And if we do so, we will have the most comprehensive, most, I think, technologically forward earthquake warning, early warning system of its type anywhere in the world.
Okay. So what is he goes on to say, this app will save lives. And he's right if people get significant warning time and know how to use it. So what's likely to happen? In this realization of the great 1906 earthquake by Brad Agard, the earthquake, let's see, how do I get this guy started? The earthquake nucleates off the Golden Gate. And let's say you're at Santa Rosa in the upper left. You've just rebuilt your house after being wiped out by the wildfire. And now 10 seconds have taken place. The strong shaking hasn't hit you yet. Let's see how long it takes for that to occur. You can see that the strong shaking is just now hitting Santa Rosa after about 25 seconds. Okay, so if it takes 5, 6, 7 seconds to detect the earthquake, to realize what we have going, and to send that message to you, does that person in Santa Rosa get 15 seconds of warning for strong shaking, and can they use it? And that's basically how earthquake early warning has been presented to us in plots like this. There's a blind zone. Those are the people for whom the shaking reaches before the message comes out. But in the position of Santa Rosa, for example, this Washington Post article suggests 15 seconds. But there's a hitch. And the problem is that all earthquakes seem to start alike. No little earthquake knows it's marked for future greatness. And what you're seeing here is that the tendency to rupture is going at about the same speed. The only difference is larger earthquakes stop later. And that means there really is no ability to know in the first few seconds if an earthquake is going to be big, and therefore if it's going to shake you strongly. So this means that if you really want to know how strong the shaking is, you may have to wait as much as 30 seconds. And if you wait that long, the blind zone is going to capture everybody in it, and so it won't work. So the alternative is to warn on very low levels of shaking. And the concept, the idea that the ultimate size isn't foreordained in a few seconds, is supported this year by work by Ide, Diego Melgar is going to talk here, and Hayes argue that 10 to 15 seconds are needed, but that's still a long amount of time. So what does this mean? In this graph by Sarah Minson and others, the S-wave, which is carrying the strong shaking, is, you can see the line going off the diagonal. Everything to the left of that in the gray area, you don't get warned, because the strong shaking has hit you before the message has. If you're to the right of that area, you get warned. And what you can see here is that for strong shaking, 20% of the force of gravity, it's extremely difficult to give you any warning. But for light shaking, you can get quite a few seconds of warning. So if you're going to try to reduce the missed warnings, then you have to warn on the prospect of very light shaking. But then that means that most of the alerts will be, if you like, false alarms. Shaking won't be damaging. It may not even be perceptible. So the key thing is, how is the public going to deal with this? If the public decides, hey, these are just false alarms, I'm tossing the app, we've lost. If the public says, wait, there actually is some shaking, I may or may not be able to feel it, this is how I develop muscle memory and get ready for earthquakes in California, then it's good news. So it's really a matter of how we communicate this to the public, given the profound limitations of any system like this. And there's a further complication to it, which is everybody doesn't need or can use the same amount of warning. So for example, if you're the Modern Museum of Art, you may really want a warning on a very low level of shaking, based on what it could do for your facilities. But if you're Homer Simpson at Springfield Nuclear Reactor, you don't want to be awakened from your nap unless you have to scram the reactor. And a reactor is built to take strong shaking. You don't do anything for low shaking. You need that strong shaking notification to make sense. So each recipient has its own needs, and we have to learn how to adapt to that. So to answer the question that I raised, how much warning? For strong shaking, it's going to be seconds. For perceptible shaking, tens of seconds. A minute is out. And we need to make sure the public understands what we can and cannot deliver, because we truly can save lives if people know how to respond. Now, Sarah Minson likes to show this image of a tornado to make another useful point. Imagine all of these people were warned of this impending tornado, okay? Well, these people got a successful alert, right? They're very lucky that they were in their basements. For these people, it's a false alarm. They wasted their time in their basement. But are they upset? No. So if we do this properly, the fact that we do not have a panacea won't hurt us. But that's what's required, getting that message. Now, this year we had a very important earthquake, the Ridgecrest earthquake, which raises new problems for us, but also solves some important riddles. And this is the event that brought us a fault out of nowhere. In heavily, beautifully mapped California, this fault was missed, 75-kilometer rupture for a magnitude 7.1 earthquake. And unfortunately, we're not alone in this respect. In New Zealand and in Japan, the same thing has happened in the last few years. And these are the 3 best mapped countries in the world for active faults. So we need to accept the fact that when it comes to magnitude 7-ish earthquakes and smaller, we don't know everything we need to know about where damaging earthquakes can be. And the problem with that is that probabilistic seismic hazard assessment, as it's practiced today, is heavily fault-based. So this exposes an Achilles heel to those methods that need to know where all the faults are. The flip side of that coin is this earthquake taught us or reinforced some very important messages about how earthquakes trigger each other and communicate. So in this calculation by Chris Rawlings, the first earthquake, which ruptured on an L-shaped brown fault there, increased the stress at the site of the second earthquake, the 7.1, which struck 34 hours later, by 2 bars, a huge amount. So there's a simple relationship between the first earthquake promoting the second. We also see places where the second earthquake shut down seismicity of the first, and that's equally important. So in this little rectangular box, you can see that in the 34 hours before the second earthquake occurred, it's got vigorous seismicity. Afterwards, it stops, and it appears to stop because it's in the stress shadow of the second earthquake. That's that blue zone. And if we look at the time series of seismicity in that little box, you can see how dramatic this change is. An order of magnitude drop in earthquakes the moment that second earthquake occurs. So static stress can turn on earthquakes and promote them, and it can turn them off. And that's what we're seeing in this earthquake. And it's not even confined to these near-fault areas. We see this writ broadly over Southern California. So now I've pulled way back, and we can see these very frail yellow lobes of increased stress, about 0.05 bars, much smaller than what I was showing you before, that reach all the way to the San Andreas at Tejon Pass and Cajon Pass. And these are associated with increases in seismicity. So you can see the yellow lobes that extend northeast and southwest, and the lobe that extends down toward Cajon Pass to the southwest are showing increases in seismicity that appear to correspond to these very small stress changes. So we have a highly tuned system that responds to small stress changes. But is this progressive earthquake sequence over? That's really the question, because the Garlock Fault has now been stressed, and it's been stressed by the same amount as the magnitude 7.1 epicenter. So is the Garlock Fault the next shoe to drop? And this is a very tricky question, because the Garlock is rotated way out of alignment to what is optimal. In fact, the Garlock shouldn't be able to move unless it's as slippery as a watermelon seed. I would call the Garlock a zombie fault. It's dead, but it doesn't know it. Now, paleoseismologists tell us it has had magnitude 7.5 earthquakes in the last several thousand years. So it appears, despite itself, to be able to rupture. And if it does, it could rupture all the way to the San Andreas, and then the game changes considerably. So this may not be over. The Garlock has had some strange responses to this earthquake, and we don't know what will happen next. Now, there's another fascinating riddle that was posed by this area that I believe the Ridgecrest earthquake solves, and that's shown here. That red line is the rupture of the 1872 magnitude 7.6 earthquake that John Muir described. And what I'm showing is the stress pattern, the static stress pattern for that earthquake, but I'm comparing it to recent earthquakes in the last 30 years. And you can see that 3 out of the 4 lobes seem to be filled with earthquakes. So, are these aftershocks 150 years after the main shock? Or, another way of thinking about this is the rupture occurred in the middle, it ruptured to the north and south, and when it reached an area that has such a vigorous background rate of earthquakes that there's no stress accumulating, it stopped. So are these soft, wet, hot areas that are always producing earthquakes that don't build up any stress, and so they stop ruptures? Or are these aftershocks? And that's where this riddle stood until July 4th, when that earthquake occurred, because you can see that a magnitude 7.1 with 4 meters of slip has landed in that southern lobe. So it had to have stress, in which case the message to me is these are aftershocks. These are very late aftershocks, and in regions that have very slow stressing rates, aftershocks can last hundreds or many hundreds of years, as was first proposed by John Adams. So this is an exciting possibility and raises a tricky issue because of how we look at seismic hazards in low deforming regions like Australia. So on the left is the last 100 years of earthquakes in Australia, and on right is the probabilistic hazard map. And as you can see, what they've just done is smooth the seismicity on the left. because none of the historical earthquakes in Australia have had anything to do with a mapped fault. None of the mapped faults have moved. They've all occurred on faults that people didn't know before. So there's the model. It's just smooth seismicity. Well, that's fine if this seismicity are background earthquakes. In other words, if you have a high rate of 4s, there's some probability of a 6 or a 7. But what instead, if seismicity in Australia, what we're really looking at is aftershocks of prehistoric earthquakes that are very long-lived, then this is not a good representation of hazard, because aftershocks are only part of the picture. Areas blue in here could very well be the next site of earthquakes. So throughout continental interiors and the eastern US, we have to solve this problem. Now we've gone from seconds. Here we're looking at 100 years of earthquakes. Now I want to look at 1,000 years of earthquakes. And that's a problem that's just been raised over the last couple of years by David Jackson. So here is the record of paleoseismic events excavated in trenches along the San Andreas system for the last 1,000 years. And you can see that there's a 100-year pause at the end of this record. So David said, is this a bias in the way paleoseismic data are collected? Are non-earthquakes being counted as earthquakes? Are we possibly even doubling the number of prehistoric earthquakes in our record? And Glenn Biazzi and Kate Scher this year analyzed this and said it's real. And further, if you have a 100-year pause in the record, then you're going to have a hell of a next 100 years with 6 large events expected. So, did we really have a pause and are we really headed for Armageddon? Or is this bias in the data in some sense? That's the question. And one way to answer that is to go to look at an earthquake model that does not use the paleoseismic data and compare it to one that does. Because if this paleoseismic data is biased with too many earthquakes, an earthquake rate model for California that uses it will be much too high compared to one that doesn't. So on the left here is the USURF3 model, the USGS California Geological Survey model, but it's been changed in a way that we're looking at just the rate of earthquakes. And that uses the paleoseismic data. And now on the right is the GEAR model, the Global Earthquake Activity Rate model, which only uses GPS strain and the last 40 years of earthquakes. So it doesn't know anything about faults or paleoseismology, and they look very much alike. In fact, at magnitude 7 and larger, they're within 4% of each other. So to me, that means that the paleoseismic data can't be too biased, or else the map on the left would be much redder than the map on the right. But that still leaves the question, do we really have a 100-year pause, and what is the next 100 years going to look like? And so let's look at where this data is coming from. It's from the blue faults, and all of the black dots along those faults are where the trench excavations are. And Biazzi and Scher argue that there's only a 0.3% probability of this occurring naturally, and that there's no dating irregularities. But what's peculiar about this is the surface cutting earthquakes that are omitted from this 100-year record. So all of those earthquakes in gray have surface rupture, but they're not counted. Well, they're part of the San Andreas system. So it seems to me this is really a counting irregularity as opposed to a paleoseismic problem. So I come out the door that it's an artifact of what earthquakes we're counting and what we're not. All of those are strike-slip earthquakes with the exception of San Fernando and a bit of Kern County. But it doesn't look to be, as far as I can tell, a dating artifact. Okay, given the problems that we have in regions that are low deforming like Australia and the problems we have in using all of the data we have in the high deforming areas, how should we be making probabilistic seismic hazard assessments around the world? And there are really 2 ways it seems to go about it. One is PSHA, which stands for Probabilistic Seismic Hazard Assessment, using the conventional method where we assume characteristic earthquakes for large events, which has been all but falsified. assigning a maximum magnitude to earthquakes, which has also been all but falsified, and slip rates for each fault, which is extremely difficult except in the best areas. So that's how it's done. That map of Turkey you're seeing behind has been done in exactly that way. That's why it's kind of an orange halo around every fault. The alternative is to base the model on strain rate from GPS and a much more recent earthquake catalog that is complete. In other words, all earthquakes above a certain size are accounted for. The benefit of the first method is you're using all available data, including a long time horizon, and obviously 1,000 years is important for our business. But the benefit of the second method is global consistency and testability. Testability is really important. No matter who makes the California model, it is not testable if you don't have 1,000 years to spare, because that's what it takes to see the largest earthquakes in the system. But the globe is 1,000 times the size of California. So you can test a global model in a matter of years. That's its strength. So what I want to do now is show you the global earthquake activity rate model and a hazard model built on it. So this is GEAR. You can see it for South America, and I'm showing it to you with the last 30 days of earthquakes superimposed. Here is Europe, and here is Asia. Okay, so it's not a hazard model, it gives the rate of earthquakes magnitude 6 to 9 everywhere on Earth. Now, what we've done at Temblor this year is build a hazard, a shaking model based on GEAR, which we call PUSH, Probabilistic Uniform Seismic Hazard, and its benefit is global uniformity. And I'm just going to show you 4 areas where we can compare the PUSH model and the conventional model. So here's the Japanese national model, also called HERP or JACIUS, and we can compare it to the PUSH model. And you can see they look shockingly different. In the PUSH model, the highest hazard is along the Japan Trench, and in the government model of Japan, it's along the Nankai Trench, and they also look different in Tokyo. Now, there's been criticism of the Japanese model, and of course, it did not foresee the occurrence of the Tohoku earthquake, and it's basically waiting for the Nankai earthquake. But that criticism seems to have some merit when we think about how this compares to a globally uniform model. Okay, let's look at Europe. So here on the left is the PUSH model, and on the right are the models that are used and published by GEM, the GEM Foundation, which are based on the standard occurrence. And as you can see, Northern Europe is profoundly different, much more hazardous in the conventional model. And there are big differences in Southern Europe too, such as Israel, which has a much higher hazard in the conventional model. Let's go to China. So in China, it's kind of amazing, even before pointing out differences, given that the model on the left doesn't know anything about faults, they look quite a bit alike. But there are differences, and the differences are in northern China and the area surrounding Beijing, which is much higher in the China Earthquake Administration model. But the flip side is Shanghai has a much higher hazard in the PUSH model than it does in the China Administration model. And the last place I'd like to show you is India and Tibet, where there are, again, substantial differences. Now, I can't tell you that one model is right and the other is wrong, looking at any specific location. But here's what I can tell you. On average, PUSH should be right because it's globally consistent. And therefore, when we see differences, we should ask ourselves the question, do we have a basis for it? Because the problem is models are built locally based on local data, local judgments, biases, et cetera, and we need a testable global standard. Now, the GEM Foundation went one important step farther, not just in terms of hazard or the amount of shaking, but in terms of what this will cost society in terms of lost economy through earthquake damage. And it's a very important achievement that they just completed. And I want to show you just a few places from this model. So the scale here is now the expected annual loss divided by local construction costs. So this is kind of the impact on their economies. And look at San Francisco and LA compared to Central America, with this enormous toll that's out there for Guatemala, El Salvador, Nicaragua, to a lesser extent, Mexico City. And if we look elsewhere, Jakarta, Kathmandu, Tehran, Istanbul, it starts to be truly staggering. My colleague Volkan Sevagan just came back from a meeting of the mayors of Istanbul, who expects 50,000 buildings to collapse in the next earthquake on the Marmara Fault. They need 20 trained rescuers for every collapsed building. This would mean they need 1 million trained rescuers. It's never going to happen. This is what we're facing. So I'd like to close this with an image that I find very arresting. This is an excavation in Cyprus. You're looking at a baby being cradled by a 19-year-old woman, and she's being cradled by a 21-year-old man. And these people were crushed by their dwelling 16 centuries ago. 30 years ago, the Loma Prieta earthquake, fortunately on a smaller scale, it happened again. When are we going to get this to stop happening? When are we going to get prepared? When are we going to be able to talk to people, despite all the things we don't know, in terms that they understand, without scaring them, without soothing them, and without snowing them? These are groups that are sending this message, communicating risk, this important process, so we won't have these collapses again in the future. Thank you.
Ladies and gentlemen, Jeffrey Todd Freymueller.
All right. One of these supposed to, which one? Okay, thank you. So I'm going to talk about subduction zones where the largest earthquakes occur. And what you see in the photo is an example of a ghost forest. There are many of these in southern Alaska. These trees were killed in 1964 by subsidence that dropped them into the intertidal zone and actually have been, in some cases, uplifted back up by post-seismic processes. So when we look at the area that can potentially rupture in earthquakes, we're talking about what we call the seismogenic zone. And the gray colors you see on the figure are patches on the plate interface that are stuck together at present by friction or by stress shadowing, but in any case, they're not moving. And so we call the areas that are not moving on the fault areas that have a slip deficit. A slip deficit just means slip that isn't happening right now, so it has to happen at some later time, perhaps in an earthquake or perhaps in some kind of a creep event. And so if we were to look over a long period of time, we would really like to be able to develop a slip budget for all parts of the fault, whether they're creeping continuously or whether they rupture and slip only in earthquakes. And so I'm going to look at two questions associated with the slip budget. The first is, does the interseismically lock, that is in between the earthquakes, big earthquakes, does that part of the interface define the potential coseismic rupture area? That is, all the gray spots could rupture, or not. And second, about time evolution. The earthquake cycle also involves a post-seismic phase, a transient after the earthquake, and how does that work and relate with transient events like slow slip events. And so I'll look at this from the case of Alaska, in particular the zone of the 1964 earthquake. This is a simulation of the 1964 displacements that was computed a few years ago. The computation here was done by Jascha Pollet for the JPL ARIA project, and you can see very large seaward motions. There's a little arrowhead here. So seaward motions of up to 20 to 25 meters during the earthquake. And in the background is the slip model that we estimated for the event before. Now, in between earthquakes, if if part of the plate interface is slipping and part of it is stuck, we can predict what we'll observe on the surface in terms of motions. And so the gray boxes are the areas on the plate interface that are stuck. And you can see that the arrows showing the motions at the surface are bigger where the gray box is bigger. So if we have measurements made on the surface, we can actually infer how much of the plate interface is moving. And if the plate interface is completely creeping like this section in between, you would see very, very little motion and very little strain. So here's actual data from Alaska, and you see some variations here that are substantial. So in the Prince William Sound area, we see large interseismic motions. Those become smaller as we move down to here. We also see these interesting motions that are back towards the trench. And I mentioned that there's also a post-seismic phase. In the case of these very large subduction earthquakes, it can last for decades. So here, the red arrows are showing you the predicted post-seismic velocities as of the time of these data. And largely, those trenchward motions we see back in the other side of Cook Inlet here are actually a post-seismic signal. If we remove them from the data, we would see what we should see over the longer interseismic period. Again, it's all largely contraction in the overriding plate. So again, you can see in this picture areas where there's a lot of motion and areas where there's only a little bit of motion. And those match up very well with the rupture pattern of the 1964 event itself. Okay, so this next slide here, on the left-hand side, first of all, you can see this is the slip model that we had estimated, and the blue patches are the areas of highest slip in that model. On the right-hand side is a slip deficit model for a particular time period from the mid-90s to mid-2000s. And the red areas are the parts of the plate interface that were not moving at that time. What you can see if you just do a quick comparison, of course, this is a fairly crude model because the data from 1964 were somewhat limited, but essentially this area of large slip corresponds to this red area here. This area of large slip corresponds to this area here. So there's overall a very good correspondence between what actually ruptured in 1964, including its very large along strike variations, and what we see in the interseismic period. The second thing we see here in red is the predicted after slip, and this is from you can see details on a poster on Friday, and you see in circles areas where we have identified slow slip events. These are transient slip events that last for a few years, kind of like a very slow earthquake. And those actually lie almost entirely within the zone that had after slip following the earthquake. So just to quickly sum up what we see about the slip budget, do the interseismically locked part of the interface, does that define the potential coseismic rupture area? The answer seems to be yes, including the along strike variations. And when we look at time evolution, we find that slow slip events occur almost entirely within the area of after slip. And even the multi-year slow slip events only involve a fraction of the locked region. So in fact, what we've estimated as the part that is not moving seems to be something that's stable over many, many decades and perhaps centuries. Thanks.
Ladies and gentlemen, Susan Bellick.
Okay, thank you. I want to take us on a journey to try to illuminate the earthquake source. So when we think about the earthquake, there are lots of details, things like the area of slip, the size of the earthquake, the actual distribution of slip on the fault plane, that are very important for thinking about ground shaking, and in some cases offshore, the tsunami hazard. And what I want to do is go through how we've learned more about the distribution of the patches of slip that have happened in earthquakes and where we're going in the future to think about earthquake processes and earthquake slip. And so along this journey, we're going to look at some examples of some observations We'll look at some seismograms. This is just an example of a seismogram from the 2011 Japan earthquake that was recorded, and then how we use this sort of data to get at images of what actually slipped during the earthquake. So go back to the fault. And then we'll talk a little bit about how these get used, getting to the hazard perspective and thinking about things like tsunami generation for offshore earthquakes. This is just an example of predicted tsunami wave heights as in response to the slip that happened during the earthquake. So if we go back to the earthquake that we have the largest earthquake recorded, the 1960 magnitude 9.5 Chile earthquake. We can see the evolution of our thinking and our understanding about the earthquake source. So for this earthquake, the area that ruptured largely comes from estimates from the aftershocks and some very limited seismic data analysis. But when we think about the estimates of slip that actually happened on the fault, this image down here, that was largely based on some limited observations of, on the ground, what's going up and what's going down. So measurements of that uplift and subsidence. But even with those limited pictures of the slip distribution, we can see heterogeneity, getting back to the previous talk in one of the slides of slip distribution and heterogeneity on the fault. So back in 1960, we had limited data sets. If we move forward nearly 30 years later, we had the 1989 Loma Prieta earthquake. This earthquake used on the order of 30 seismic stations, pretty respectable number for the time, to get at estimates of the slip that happened on the fault. So again, we get back to this idea of some slip heterogeneity, slip on the fault. But we've been evolving the amount of data and the types of data that we collect over time. And we can jump ahead and look at another earthquake, the magnitude 9.1 Sumatra event in 2004. And this earthquake was recorded with a variety of different data sets. One example shown here, this earthquake was captured by the IRIS Global Seismic Network, which is a set of high-quality permanent seismic stations around the globe. And that data shown here was used to produce models of the earthquake slip, like the one shown next to it. For this event, we also had regional GPS data, and so we could look at the static displacements and introduce those into models to get yet another view of the earthquake source. During this time, we were also getting data from very high-quality seismic arrays, like the example in Japan, the HyNet array. And these large arrays allowed us to be able to look at the distribution of high-frequency energy, again, back to the fault. So we can look at the spatial and temporal variations of that rupture over the several minutes of that rupture. And this event triggered the widespread use of this back projection technique. And so we have a lot more pictures of different earthquakes, seeing how these slip variations happen on the fault. So where are we going? Where are we now? We continue to collect a wide range of data and use that data to get at pictures of what the slip was on the fault. There are 3 examples here using seismic, geodetic, or tsunami data. But more often, we're starting to integrate these data sets and jointly invert multiple data sets for the slip on the fault. And this example here, again, for the 2011 Japan earthquake, combines multiple different data sets to get at a picture of the earthquake slip. So where are we going in the near future? Lots more observations. So on land, we can reasonably deploy hundreds of thousands of seismometers to get better pictures of the earthquake source. This is just an example of hundreds of sensors recording tiny earthquakes in Oklahoma to get at a picture of the earthquake source. We're starting to get new offshore capabilities on the geodetic side to provide some additional coverage, especially in subduction zone areas, to get at information about the potential slip in the offshore areas. And then on land and offshore, we're starting to get the potential for even more observations. This is just an example of a fiber optic cable that is located just south of here. This fiber optic cable was used to image the Earth structure, but it also captured seismograms from, or information, seismic waves from a regional, local earthquake. And I think as we get more and more data, one of the challenges is going to be dealing with this data. Lots more observations. It's going to require additional data handling techniques and integration techniques to be able to understand this data in the context of the earthquake source and tie it back to the hazards. Thanks.
Our next speaker is Diego Melgar.
Does anybody know any jokes?
Three seismologists walk into a bar.
Ooh, that's all the way at the end. Let's back it up. Okay, I want to spend my 5 minutes dwelling on something that Ross brought up, and in the context of earthquake and tsunami early warning, and that is to distinguish between the underlying process, in this example, a supercell, a storm, and the associated hazards with that process, which would be the rain, the sleet, the hail, the lightning, and the tornadoes associated with that. In seismology, of course, the underlying process is the earthquake, slip on a fault, and the associated hazards are strong shaking, shown here, shaking my house there in Eugene, and the associated tsunami that comes with that coseismic dislocation. Now, for a long time, unless you've had very dense geophysical networks, it's been very difficult, if not impossible, to measure the hazard everywhere. So what I would call the traditional warning methods that evolved in the 80s and 90s take a proxy approach, and that is we try to infer things about the earthquake itself from sparse measurements such as the hypocenter, the magnitude, and its extent, and then from that knowledge compute or infer the shaking, the hazard, and the tsunami amplitude. And if we ask the question, how well do the algorithms do based on this proxy approach, and how well do we measure earthquake magnitude and other features of the events, we actually do quite well, especially if you take into account algorithms that can capture many kinds of data like seismology and geodesy. In this example, this is a simulation, but the situation is similar elsewhere. For a simulated Cascadia 8.7, by about 60 or 70 seconds, we get the magnitude bang on the nose. So that there is good news. But really, what we care about is not the earthquake. As seismologists, we do, but people do not. What matters is the hazard, the intensity of shaking and the tsunami amplitude, and that is really tricky. In this example from the Long Beach Array that many of you might be familiar with, I want you to focus on the shake map there on the right-hand side. This is a magnitude 2 array on an earthquake on a very tight array. And look at the richness and the diversity of the hazard just from that tiny earthquake, sometimes at the scale of city blocks. So we started asking new questions. How well do we do in earthquake early warning when we grade ourselves in hazard space? And Menandrin Meyer and Sarah Minson and many others have started tackling this question, and the answer is it depends. It depends on what shaking thresholds we set for ourselves, and we also started talking about the user. This is a word that is, I think, relatively new to warning. What does the user want? If the user sets a certain level of threshold, the warning that they're going to get, these true positive alerts, are going to be a certain proportion of all the alerts, and they're going to see certain warning times. If they set a different level of threshold, they might see more false positives or more false negatives, or increased numbers of true positives and true negatives. So we've started having that conversation now. And that's also triggered the development of new algorithms that completely disregard the source, pioneered perhaps in Japan, where you see this example of what the shaking looks like now for some point in time during the Tohoku Oki earthquake. If I know that shaking and I know some data science and some physics, I can forecast that shaking forward in time and ask the question, based on what I see now, what will the shaking be 10 and 20 seconds into the future without actually caring about the earthquake? And that's shown here in the difference between the black, the observed shaking in Tokyo, versus the blue, which is what was forecast well, and where do we need to improve. So this is a new paradigm for warning, and with densifying networks, this is the state of affairs in the west coast of the US, and if we bring to bear simulations as well, and if we start to think about data science and machine learning that you'll hear about to death if you go into the earthquake early warning sessions, we're finally in a position where we don't have to talk about the storm. We don't have to talk about the earthquake. We're finally, to answer Ross's call to action, we can finally say something not about that earthquake, but about the weather. And that's where we're going in the field of warning. Thank you.
Our next speaker is Marco Maria Scuderi.
Okay, so in the next 5 minutes, I'd like to bring you into a journey. It didn't start. Any joke? Okay, not yet. Okay, so in the next 5 minutes, I'd like to bring you in a journey in the world of the laboratory and show you what we can understand about faulting, highlighting how experiments can provide exceptional insights into the physical processes that characterize the seismic cycle. No? Okay. So earthquake seismology is in the middle of a revolution because with the discovery of slow earthquakes, our understanding of how a fault can slip has been shaken to the core. In fact, nowadays, slow earthquakes are observed worldwide and they are recognized to play a fundamental role in the slip budget of seismogenic faults. However, one of the fundamental questions that we still cannot address is why they are slow. So what is the physical mechanisms that keeps the velocity not accelerating up to seismic velocities as it happens for regular earthquakes? So in the last 50 years, laboratory experiments have created the foundations for our understanding of the physics of frictional sliding and provided the basis to build theoretical frameworks to model the seismic cycle. So since nature is beautifully complicated, the advantage that we have in the laboratory is that we can control the boundary conditions around the fault and we can access the details of the fault zone deformation with unprecedented resolution in order to isolate the physical mechanisms that are at play during deformation. Only recently, in the last 4 years, by combining a theoretical approach based on friction law and laboratory experiments, we were able to reproduce the full spectrum of fault slip behavior, from aseismic slip to slow earthquakes up to regular and dynamic earthquakes. So the ability to systematically reproduce different styles of faulting as it is observed in nature has marked the beginning for a series of observations that shed light on the physical processes that characterize the seismic cycle. So in the lab, we can instrument a fault with a variety of sensors positioned very close to the actively slipping zone, and we can unveil a number of signals that the faults produce during the seismic cycle. In fact, by systematically measuring the variation of seismic wave velocity, we were able to detect some clear slowdown in the velocity preceding the earthquake stress drop, which give us some hope for future application in nature to implement early warning system. Furthermore, we can also listen to what the fault has to tell us. In fact, by measuring acoustic emissions from an exceptionally dense array of miniature seismometers at extremely high frequency, we can build a large dataset that we can use for the training of machine learning algorithms. So a little controversial observation, but a very exciting and promising line of research is that machine learning revealed us a previously unknown fundamental relationship between the sound that is emitted by the fault during its deformation and its physical state at all times, with the ability to predict the time of failure of laboratory earthquakes. So, coupling between the seismic signals and the careful measurements of rheological properties of a fault during the seismic cycle has the potential to unveil the physical processes at the origin of the earthquake slip. However, the Earth is very complicated, it's a very complex system, and it is not as in the laboratory. And faults are highly heterogeneous, and this is pushing us to explore more realistic boundary conditions and more realistic fault rheologies as observed in the field. So heading toward this direction in the next 5 years, we will build a team that will work on machine learning to predict laboratory earthquakes by developing new state-of-the-art laboratory apparatuses and combining with the near-fault observations in order to advance our knowledge on the physical processes that leads to earthquake faulting. Thank you.
Oh, wait, where's...
Hi, everybody. I'll be talking about modeling earthquake source processes. As we have seen from the previous presentations, clearly earthquake source is a very challenging problem, and this is in part due to the fact that multiple spatial and temporal scales are involved, and over those scales, multiple couple physical and chemical factors are acting. And in particular, one of the advances over the recent years have been this realization that pronounced shear localization occurs and a wide range of conditions where the shear in the fault cores can occur at sub-millimeter scales, and then it affects both the seismic, it affects both the dynamic rupture and also how the interseismic period works. So to study the recent advances in this area, understand the future, there was this NSF-supported workshop. You can download the report from this link at the bottom, and multiple observational laboratory and modeling scientists contributed to it. And in particular, the report highlighted the important advances in modeling earthquake source that have been done from the numerical perspective, from the discovery of the super shear rupture, which was actually done in models and then found both in the lab and for natural earthquakes. Also modeling of dynamic ruptures over complex fault geometries, highlighted by recent earthquakes that occurred. Enhanced understanding of where the destructive high-frequency radiation, destructive for buildings and infrastructure, comes from, and in particular, it may come from fault roughness, and the physical basis of slow slip events that Marco has talked about, as well as emerging attempts to link the geodynamic scales of millions of years to the seismic outcomes. To give a more detailed example from the work in my group, we tried to understand how earthquake sequences in slow slip occur on these highly localized shear zones that have been characterized in the lab. So we have some quantitative relationships for them. And this movie shows the slip velocity across a generic strike slip segment, with the black showing zones that are locked, blue are creeping at the long-term tectonic loading rate, and the seismic velocities are shown in yellow to red. And so what we can see is that the bottom transition from the creep below to the locked zone above precipitates this microseismicity in this particular model, enhanced by some heterogeneity assumed. And so these small events keep occurring at the bottom of the seismogenic zone until one of them, from a very small scale, nucleates a large rupture, and that ruptures the entire segment, and then there is post-seismic slip, and then the fault is being reloaded, and the cycle or the life cycle of this fault will repeat. And so the relationships that make the simulation possible are shown in, some of them are shown in the bottom. As an important advance was the laboratory-derived rate and state friction that came from the laboratory, from the pioneering work of Dietrich, but many other researchers, as well as this notion that shear heating during rapid slip can promote enhanced dynamic weakening, in particular by thermal pressurization of pore fluids. And so the results of this movie that I've just showed you are summarized in this panel. On the right, where we see how the large slip in a typical large event shown in color corresponds to these blue dots and red dots that represent interseismic and aftershock events, respectively. And so we can vary the properties of the model and see how, if we assume more enhanced dynamic weakening in this particular model and deeper penetration of the large events as the result, how we can completely shut down that microseismicity in the interseismic period at the bottom of the seismogenic zone. And this corresponds well to observations from mature strike slip faults around the world. In particular, what you see here is the San Andreas fault with the colored dots representing microseismicity, and some have a lot, especially at the bottom of the seismogenic zone, like the simulations show, and some have very little, so they're quiescent, and there is a good relationship between that and the large earthquakes, the largest earthquakes that occurred in the past, which presumably penetrated deeper and shut down microseismicity for hundreds of years to come. So we can use the same models to study other problems, such as, for example, physical reasons from low heat, low stress operation of mature faults, where the two main hypotheses is that it occurs either because the faults are statically strong, like the high Byerlee friction, and then dynamically weak, like in the models we're exploring, or perhaps the faults are chronically weak, say due to persistent fluid overpressure and low friction. And there is a complicated plot on the right, but the important thing is that we seem to be able to distinguish between these and other models because of how much radiated energy is created. So please come to a poster for details. So to summarize, modeling allows us to put all these scales together and to understand interaction of faulting at different scales and augment full observations by laboratory and theoretical findings, and in particular study the effect of small-scale proteins on large-scale rupture. And what we would want to do from there is predict the source components of source ground motion, improve our understanding of the potential large extreme events, and quantify uncertainty and key gaps in our knowledge. We need improved constitutive relationships for that, and they will come from integrated field, observational, laboratory, and numerical models. Thank you for your attention.